Welcome to The Explainer. Today, we're diving deep into a field that's, well, the very bedrock of modern math and computer science, proof theory. It's an incredible story, really. It starts with a crisis of certainty, features a stroke of pure genius, and ends with a discovery that connects pure logic to the software you use every single day.
So, here's how we're going to break it down. We'll start by going back to a time when a major crisis shook the world of mathematics right to its core. Then, we'll meet the thinker who came up with a totally revolutionary solution. From there, we'll dig into the main goals of the field he created, and we'll wrap up by revealing this surprising and honestly super powerful link between formal proofs and computer programs.
All right, let's set the scene. We have to rewind to the early 20th century. For centuries, mathematics was seen as the one thing we could all count on, right? It was the gold standard for certainty and truth. But all of a sudden, it started having a profound identity crisis.
And at the very heart of this crisis was this deeply unsettling question that mathematicians started asking themselves. How can we be absolutely 100% positive that our proofs are actually sound? How do we know for sure that somewhere down the line they won't lead to some kind of devastating contradiction? And look, this wasn't just some philosophical coffee talk. The discovery of actual paradoxes sent shockwaves through the whole community. Take Russell's paradox, for example. It asks a simple question. If you make a list of all the lists that don't contain themselves, should that list contain itself? No matter how you answer, you end up in a total contradiction. It was like finding a giant crack in the foundation of a skyscraper. It made people doubt the integrity of the whole building. So, in response to all this chaos, the legendary mathematician David Hilbert launched this incredibly ambitious rescue mission, which we now call Hilbert's program. His goal was, well, nothing less than putting all of mathematics on a perfectly logical, totally unshakable, and provably consistent foundation. The idea was to make it forever safe from contradiction. But you know what's funny? The key breakthrough didn't actually come from finding new rules or axioms. No, it came from a completely fresh way of looking at the problem, all thanks to the brilliant work of Gerhard Gentzen in the 1930s. He decided to stop looking at the individual steps and instead study the very shape of logical arguments themselves. And this was a massive shift in thinking. See, before Gentzen, proofs were basically just a straight line of statements. You checked that step 2 followed from step 1 and 3 from 2, but you couldn't really see the big picture. But Gentzen came along and introduced these new systems that let you see a proof as a kind of tree, with the assumptions as the roots and the conclusion as the trunk. All of a sudden, the entire logical flow became transparent and something you could actually analyze.
Now, the crown jewel of all of Gentzen's work was something called the cut-elimination theorem. This was his masterstroke. What it proves basically is that any logical argument, no matter how ridiculously complex or roundabout it is, can be systematically boiled down to its most direct form. It strips away all the unnecessary detours or intermediate steps, what proof theorists call cuts.
Here's a good way to think about it. A proof with cuts is like taking the winding, scenic country road to get somewhere. A cut-free proof is the direct superhighway. So cut elimination guarantees that a proof takes the absolute most efficient path from A to B. And this doesn't just make the proof more elegant, it makes it way, way easier to analyze for consistency, which was the huge problem Hilbert was trying to solve in the first place. So this revolutionary new ability to dissect and simplify the very structure of a proof, well, it gave birth to a whole new field, proof theory. And it gave mathematicians this powerful new toolkit to go after some really fundamental goals. And this new way of thinking really opened up a whole new world. Some of the goals were, you could say, defensive, like consistency proofs, which was Hilbert's original dream of making sure a theory wouldn't ever contradict itself. Others were about measurement, like using ordinal analysis to basically assign a power level to different mathematical theories. But then you get the really forward-looking goals, the creative ones, proof mining, which is about extracting hidden algorithms from proofs, and automated deduction, which laid the groundwork for computers that could actually reason for themselves. Okay, and this is where the story takes a wild, completely unexpected turn. What started as this very philosophical quest to secure the foundations of mathematics, it ended up revealing this deep, hidden connection to, of all things, the world of computer programming. This incredible insight is often called the Curry-Howard correspondence, or just proofs as programs. And it reveals something mind-blowing, that a logical proof and a computer program are, at a deep, structural level, the same thing. A logical statement, a proposition,
corresponds to a data type in programming. And a proof of that statement? It is literally a program that produces a value of that type.
So think about what that means. That mechanical process of simplifying a proof, what Gentzen called cut elimination, is identical to the process of running a program. It isn't like computation, it is computation. This discovery was an absolute game changer. It became the theoretical foundation for whole families of functional programming languages and modern type theory.
So after all of this abstract, foundational stuff, you might be wondering, okay, why should I actually care about this? Well, because its impact is pretty much all around us.
Seriously, the ideas that grew out of proof theory are not just theoretical curiosities. They are the engine behind the very type systems in modern programming languages that make our software safer and more reliable. They power the automated reasoning tools that verify a new computer chip is designed correctly before it costs millions to manufacture. And they're totally foundational for artificial intelligence and logic programming, fields trying to build machines that can reason and solve problems on their own.
So as we get better and better at formalizing and automating the very fabric of logical deduction, we're left with this really fascinating and kind of provocative thought. If a proof is just a type of program, and we're getting really good at teaching machines to write programs, what are the ultimate limits of automated reasoning? Could we one day build a system that not only proves the things we already know, but actually discovers entirely new fields of mathematics all by itself?